Topic today is the bit error rate analysis, the bit error rate analysis of antipodal signals. Specifically, we would see the probability of error, the expression for probability of error. So we would like to derive the mathematical expression for the probability of error, and we would see the the bit error rate analysis. The bit error rate analysis in additive wide Gaussian noise channel with maximum likelihood detection. So we would see that if we have an optimum receiver, how many bits would be in error. Bit error rate means the bit errors. If you transmit some bits, and you get due to this noise you get some error due to this detection error probability. Due to the error probability of detection, you get some errors, right? So we would see specifically that what is the mathematical expression for the error probability, and for a specific signal to noise ratio, what is the bit error rate. So we would specifically see the bit error rate in AWG, in additive wide Gaussian noise channel. We assume that the noise is zero mean with variance sigma square. So today we would assume that the noise is not having sigma equal to 1, it is sigma square, any general value, sigma square, any value. Maybe 1, maybe less than 1, maybe greater than 1. So you would keep it just sigma square. The noise variance would be kept as sigma square. And keep in mind the noise variance is directly the noise variance represents the energy of the noise, right? So if it is higher, it means more noise. If it is lower, it means less noise. And we would specifically see the bit error rate plot. So let's start with some basics, and assuming that we have a sequence of ones and zeros available, a random ones and zeros sequence, and we are discussing binary signal transmission, of this ones and zeros. So for a binary one, we transmit s of t, suppose, and for a binary zero, we transmit minus s of t. We have just observed that this is these are the antipodal signals, the two waveforms. If you want to draw the waveforms, you can draw it. For simplicity, it can be assumed as a pulse, right? A pulse. S of t with a magnitude plus unity. Similarly, minus s of t would be a negative pulse existing from 0 to t, and this is with magnitude. This is minus s of t. So suppose we are transmitting these two basement pulses for a binary 1 and a binary 0. So all this data can be transmitted over the noisy channel using these waveforms. You can assume these as voltage waveforms, right? So it's just like your voltage signals which you are transmitting from the transmitting end using binary signal transmission, or we are using these antipodal signals, the signals with opposite polarity, during this time interval 0 to t. So when we transmit the signal with this opposite polarity, what we expect at the receiving end in a noisy channel, that we have the received signal r of t, which is actually either plus or minus s of t plus the noise, additive wide Gaussian noise, which add up to our signal. So this is our received signal, Uh, well, when we pass this received signal, suppose we start with by assuming, let's assume, let S of t is transmitted, right? Suppose we say S of t is transmitted. So when S of t is transmitted, your R of t would be S of t plus noise. And if you pass it through the correlator, you would expect your sample value R, which would be equal to the energy of the signal plus a noise term. And we know how to derive the PDF of R, right? And we can draw the PDF of R. It is just a shifted PDF towards E. So if you are, it is a Gaussian and with mean E. Right? You can draw the PDF of R when S of t is transmitted. We did it in our previous lecture, so I would not repeat that one. You can use the knowledge of the transformation of random variables to derive this PDF. So we have this PDF of R, which is E plus N, right? Which is E plus N, and we actually we know that R of t, the correlator receiver, the correlator receiver give us it gives us this signal. The correlator receiver gives us this signal. Or this is actually the sample value which goes to the maximum likelihood detector, and based on this value of R, the detector decide whether S of t is transmitted or minus S of t is transmitted. So we have this knowledge now, and if we see that if we assume that minus S of t is transmitted, if we assume that if minus S of t is transmitted, then your received signal, R is minus E plus N, right? So we have these two received signal based on the transmission of a binary 1 or a binary 0. Now we would be interested in finding out the expression for the error probability, the mathematical expression for the error probability, or in other words, if you transmit many ones and zeros, maybe hundreds of megabits, binary ones and zeros, you may expect that some of those bits are not received correctly, but though the error which occurs, it occurs due to this noise. It occurs due to the noise which is present at the receiver. So we are interested in finding out the mathematical expression of this probability of error, or the chances of error, right? The probability, that what is the probability that, based on that knowledge, we would see, we can we can say that, okay, if your SNR is let's say 10 dB, this would be the probability of error, that you would get some error. And we will use that knowledge later on. I would like to explain it with the help of an example. But let's try to derive the mathematical expression for the error probability. Now, having this knowledge, if we draw the conditional PDF of R, as we did in the previous lecture, we can draw the conditional PDF of R, and this conditional PDFs are also known as the likelihood function, right? So we have the conditional PDF, and either the mean is E or it is minus E in this case, and we have a threshold which is here, and this threshold is eta. Let me give it the name eta. Now we can clearly see that if we have the 2 points E and minus E, this threshold should be equal to 0, right? So let me write 0 instead of eta. Let me write 0 here, which is just the midpoint between these two. The midpoint between these two means, these two expected values of these two means. Now this is the PDF. This is the conditional PDF of R, given that S of t is transmitted. Given that S of t is transmitted. And this is the conditional PDF of the received signal R, given that minus S of t is transmitted, right? Minus S of t is transmitted. So we derived these conditional PDF in the previous lecture while we were discussing the maximum likelihood detection. So now we would use that knowledge to get the probability of error. Now how we can let's try to understand the error condition. Suppose you transmit S of t, and you transmit, suppose S of t, you transmit S of t, and the value we would expect that if there is no noise, then we would get this point, right? We would get this point, which is the energy of the signal, because your R is equal to, this is Rx, this is the axis of R. So your R is actually equal to, if you transmit S of t, your R is E plus N. If no noise, this term is 0, so your R is equal to E, and you are getting this point. If suppose if we get this point, we would be pleased with it, because with this point we can based on the likelihood function, we can say that this point actually represent S of t, and we can say that okay, S of t is transmitted, or a binary 1 is transmitted. So we say that the binary 1 is received. At the receiving end, we'd say that with this value we can clearly say that a binary 1 is received. Now all the points which are towards the right of this axis, if we receive any of these points would be detected correctly if S of t is transmitted. If S of t is transmitted and you get this point, based on the likelihood function, it is straightforward to decide that this point belongs to, this point actually belongs to this conditional PDF, not this black one. So for all these points we detect correctly S of t. If S of t is transmitted and we get any of these points, S of t would be detected correctly based on the likelihood function. But what would happen if S of t is transmitted and you get this signal point? It's towards the left of this threshold, to left of this 0. Now you can clearly see that for this signal point, the likelihood, it is more likely that this signal point, more probable that this signal point belongs to the black PDF rather than the blue PDF, right? It intersects the blue PDF as well, but this value on this axis, vertical axis, is smaller than the value of the black PDF. Or you can say that this is suppose this is L1, this is L2. So you can clearly see that if S of t is transmitted and you receive this point, which is towards the left of this threshold, for this particular point L1 is greater than L2, or it is more probable that this point belongs to this black PDF than the blue PDF. It is more probable. So the detector would decide in favor of minus S of t. Although the transmitter has transmitted S of t, but the point which is received due to this noise factor, due to this noise, the point which is received falls towards the left of this zero or this threshold, and if the point falls towards the left of the threshold, the detector, the optimum detector or the maximum likelihood detector decides that minus S of t is transmitted because it is more likely. So it decides in decides on the basis of the likelihood. So it is more likely that this point is minus S of t, and the optimum detector would take a wrong decision. Right? The optimum detector would take a wrong decision. So for all those points which fall towards the left, right? Now keep this in mind, assuming that the transmitter has transmitted S of t and the point is received towards the left, any of these points which is received towards the left, they would contribute in the errors. Now you transmit a binary 1 and the receiver detects a binary 0, right? Because the point noise is high, this noise term is so much high that it causes this point to appear towards the left. Now all the points which appear towards the left are declared as minus S of t or a binary 0. So the transmitter transmits S of t or a binary 1, but the receiver declares that it is minus S of t or a binary 0. So this contributes an error, right? This contributes an error. So this is the error condition, right? This is the error condition. Now we can write, based on this knowledge, we can write the expression for the probability of error. Now how we can write it? Let's see. We can say that probability of error. You can say that okay. Let me write it here. The probability, we can say that the probability of error, when the error occurs, the chances of error is the probability that the received signal is less than 0 given that S of t is transmitted. When S of t is transmitted. So this would be the probability of error. This would be the probability of error expression. So probability of error expression is probability that R is less than 0 when S of t is transmitted. Similarly, you can find out the probability of error expression when minus S of t is transmitted. So all the values which are you can write the expression, because in that case all the values which fall over here towards the right, if you transmit minus S of t and you received any points towards the right, that would contribute an error. So you can similarly say that probability of error is P of R, probability of R greater than 0 when minus S of t is transmitted. So based on this expression, now we can derive the probability of we can derive an expression for the probability of error. So we specifically, let me write that one. We specifically said that the probability that R is less than 0 is actually the probability of error when S of t is transmitted. When S of t is transmitted, right? So this gives us the probability of error. Now we know the expression of this. Now we would like to use the the PDF given for the value of R. So we are already familiar with this PDF and the PDF of R. Let me specifically write the PDF of R. So if I write the PDF of R, given that S of t is transmitted, that is actually equal to 1 over under root 2 pi sigma square. Now we keep the variance sigma square, right, then unity, right, to be to generalize it. So e raised to power minus r minus e whole square over 2 sigma square. So this is the probability of R. This is the PDF of R when S of t is transmitted. Right? The PDF of R when S of t is transmitted. The conditional PDF. We can always draw this conditional PDF, which we did in our previous lecture, and we said that okay, this is suppose this here it is 0 and this is E, point E, and this is P of R given that S of t is transmitted. Now all the points towards the left, we transmit S of t, we receive some point which fall towards the left. Any of these points, they contribute an error, which we write over here in this expression, that probability that R is less than 0. It is the probability of error. So how we find this probability? We need to integrate this black curve, this conditional PDF, from minus infinity up to 0. So we actually need to integrate this area. And this area actually gives us the probability of error when S of t is transmitted. So when you transmit a binary 1 and you would get a 0, what's the chance to get a 0? It is the integral. It is the integral of this black curve from minus, in this range, from minus infinity to 0. So if we are interested in finding out the mathematical expression, we already have this we already have the PDF. So we would integrate this PDF. We would integrate this PDF from minus infinity up to 0, right? Up to 0 dr. So let's try to solve this integral and find out the mathematical expression for the PDF of the mathematical expression for the probability of error or the bit error rate. Probability of error or the bit error rate. So our probability of error is equal to minus infinity to 0 conditional PDF of R given S of t dr, right? This is, we have to integrate this. So if we plug this value minus infinity to 0, and the PDF of R is 1 over square root 2 pi sigma square e raised to the power minus r minus e whole square over 2 sigma square dr. We need to integrate it. Now here, keep this in mind. We can just put this constant outside. This is 1 over 2 pi sigma square minus infinity to 0 e raised to power minus r minus e whole square over 2 sigma square dr. Now to find out this probability, I would like to specifically give you a hint that whenever solving this type of integral, we always try to write this exponential term. This is an exponential term. we write it in the form of we try to change this variable in such a way that our exponential term can be written in the form of square of the variable over 2. Now I will give you the benefit. I will tell you what's the benefit of changing this variable in the end, right? But for the time being, we have to change the variable r. We have to change the variable. Now it is probability of error is the function of r, right? It's the function of r. We have to change this variable r so that we can write this exponential term as the square of the variable over 2, right? The square of the variable over 2. So let's change the variable, and if we want to write it as the square of the variable over 2 in this form, I would have to choose my variable y. Suppose instead of z I use y square over 2. So I have to choose y variable, which should be equal to r minus e over sigma. So if I choose this variable y, which is just by observation, I want to write it as y square over 2. So we can write it in the form of y square over 2 if we choose y equal to r minus e over sigma. So now you can say that you can clearly see that this is equal to y square over 2, right? This is equal to y square over 2. So when we change the variable, instead of r minus e over sigma, we would write y. So dy is equal to 1 over sigma dr, right? So we are changing this variable. So dy is equal to 1 over sigma dr, right? Similarly, we have to change these limits as well. So if the limits of r, if you see the limits of r is from minus infinity to 0. So we are interested in the limits of y. So y would be if r is minus infinity, if you substitute minus infinity r here, if r is minus infinity, then y would also be equal to minus infinity, right? And if r is equal to 0, y would be equal to minus e over sigma. So these are the limits for y. So we change the limits of y, keeping in view the limits of r. So the limits of y can be changed using this expression. So these are the limits of now we have all the values. We have all the for the conversion for this change of variable. We already have all these. The limits are available, and we also find this dy. So we can rewrite this expression, probability of error expression, the probability of error expression, in terms of a new variable y. And if we try to write it as a new variable y, we can say that okay, our probability of error with this new variable would be equal to 1 over 2 pi sigma square integral. Now we have to put the limits of okay, before substituting the integral, let me write e is equal to minus y square over 2, right? We can write e is equal to minus y square over 2. Now we have dr in the expression, so instead of dr we would write this value. So dr is equal to sigma times dy, right? So instead of dr we would say sigma times dy, right? And the limits from when r is minus infinity, y is minus infinity, so y is minus infinity. When r is 0, y is minus e over sigma. Minus e over sigma. So from minus infinity to minus e over sigma. So this is these are our new limits, minus e over sigma. Now what we can do, you can clearly see that this sigma cancel out with this square, this sigma, because this is under root sigma square. So when square root and the square root cancel, so you are having sigma in denominator, you are having sigma in the numerator, both cancels out. So your new expression, your probability of error expression reduces, it reduces to, let me rewrite it. Your probability of error expression, is 1 over square root 2 pi minus infinity to minus e over sigma e raised to the power, it's simplified now, y square over 2 and dy. This is the expression for the probability of error. Now if we compare it with the we can compare it with the standard Q function which is available to us. And the Q function, let me give you some details of the Q function. Let me give you some details of the Q function. This expression is now equal to the Q function. Let me rewrite it as a Q function, and then I would explain what is this. This integral is known as the Q function. We call it the Q function. We call it the Q function of minus. We call it the Q function of e over sigma. Actually, this one, the Q function of this value, e over sigma. So you can write the Q function as this integral. This is the same as this integral, right? The Q function, and your MATLAB or Octave can compute your integral, this Q function or the integral for different value of e over sigma. Now we are interested, E is the energy of the value, the energy of the signal. E is the energy of the signal. So our integral, the probability of error, depends on the energy of the signal. Let me give you some details of the Q function. Actually, the Q function, if you observe, it is the Q function is monotonically decreasing function, and if we write the expression for a Q function, we say that it is, let me recall it. The Q function using the knowledge of the from some books, and I would like to give you the expression for this Q function. Let me rewrite the expression for the Q function. So I would like to write the expression for the Q of x. Actually, Q function of Q of x, and Q of x is 1 over under the root 2 pi. It is actually x to plus infinity. It is x to plus infinity e raised to the power minus t square over 2 dt. This is a Q function, right? This is a Q function, Q of x. So if you see Q of x, it is given by this expression. Now what does this expression represents? What does this expression represent? Now the constant if you observe these limits, actually the problem which you can see in this one and the above expression are the limits. The rest is okay, because you have q of x, and x is given here in x is the lower limit, while we have an upper limit there, right? We have written it in the form of q of x and we have taken the upper limit. The rest is okay. We have the square of the variable over 2. So this is the square of the variable over 2 dt. So there we have y square over 2 dy, right? So the rest is okay. We are just concerned about these limits now. So if you observe this PDF, why we write it in the form of q of x, I'm just trying to explain that one. If you observe the PDF of noise, which is the standard Gaussian PDF, the PDF of noise or the standard Gaussian PDF, it is 1 over 2 pi e raised to the power minus x square over 2. This is the PDF of noise, right? So if you want to draw this PDF, you can draw it. You can draw it on a single page. You can draw it. This is the value of x, and you have a 0. It's a 0 mean. You can clearly see the mean is 0. For a 0 mean PDF, we have just x square. Otherwise the mean would appear in this exponential term, x minus the mean value. So we have 0 mean. This is p of x. And now what does that integral x to infinity? If we see this integral, which is integrating actually this PDF from it's very similar to this PDF, 1 over under root 2 pi raised to the power minus t square over 2. So this is actually the integral of this PDF from x to infinity, right? X to infinity. If you observe in this expression q of x is the integral of this PDF from x to infinity. So we can say that if we have a Gaussian PDF which looks like this, standard Gaussian, with sigma square being unity, if we have this Gaussian PDF and we integrate it from x to infinity, x to plus infinity means some value here. Suppose this is some value of x, and we integrate this area. So this integral is known as q of x. This integral is known as q of x, which integrate the standard normal curve from x to infinity. This is the q of x. So if your x is greater, now keep this in mind, if your x is greater, the value of q of x, which is the integral from x to infinity, right, this area would be smaller. So if you are if this value is greater, is the value of x. Suppose this is x1. So we have q of x1. This is x1. No, we are using x as a variable, so let it be x1. So x1 is this point. If your x1 is greater, so q of x1 would have a smaller value. Or it means that if your x1 is greater, your this area is smaller, because this integral gives us this area, right tail. We call it the right tail probability. So this area is smaller. So when this area is smaller, it means we have our expression is in the form of q of x, right? So it means our probability of error is less chance of error if x is greater. And you can see that your x is actually the x variable in our expression depends on the energy of the signal. So more energy means less errors, so it is obvious. Now in that expression we have taken the minus infinity to minus, our expression is from minus infinity to minus e over sigma. Now let me correlate it here. Now if I take this integral, because this is the standard normal curve, right? Half of this curve is here, half of this curve is here, standard normal. So if I take this integral, this is q of x1. I can take the same area selecting a minus x1 here. So minus infinity to minus x1 would integrate this area, minus infinity to minus x1, and because the curve is symmetric, so this area is same as this area. That is why we can write, if we have either the integral of this area or this area, both can be written as in the form of q function, q of x1. So we can, q of minus x1 is actually equal to q of x1, right? Q of minus x1 is same as q of x1. So in the above expression, we had, let me once again state this, because we have, this is a crucial point. If you integrate this curve from x1 to infinity, you would get this area, which is the right tail probability. Or if you integrate it, because this point is 0, if you integrate it from minus infinity to minus x1, you would get this area, and these two areas are same. So we can also write that this PDF, integral of this PDF, we have taken r here, integral of this PDF from minus infinity to minus x1 is same as, it is equal to the integral from x to plus infinity dr, right? And our expression of probability of error expression actually is in this form. In the above, our probability of error expression is in this form, which is same as this one, and this can be written as, sorry, this is x1, this can be written as q of x1. That is why we have taken this, our expression, we have written our probability of error expression as q of minus e over q of minus we have written it as a q of e over sigma, right? This is our expression, probability, the expression for the probability of error. So this is the q function and expression for the probability of error, which is directly related. It is directly related to the energy of the signal. Now you can see the error probability, or the chances that we will get an error or a one would be detected as a 0, depends on the energy of the signal, and this the variance of the noise, right? So we have in this expression, above we have the energy of the signal, below we have the standard deviation of the noise. We know that the noise is actually the variance of the noise is it corresponds to the energy of the variance of noise corresponds to the energy of the noise. So let's try to represent this as the this is actually energy of the, in the numerator, energy of the signal, in the denominator a term which is related to the energy of the noise. Let's try to find out this term, this sigma. Let's try to find out this sigma now. So if we observe the sigma, how do we find the sigma? Let me because the sigma noise, it is related to the variance of the noise, right? So sigma square, sigma square, it is the the expected value of that noise term which is present the second moment of the noise. Why we call it the second moment of the noise? If you recall your the previous expression, the moments, it is the second moment. Our signal R is energy plus noise, right? And this is a random zero mean Gaussian process. When it is a zero mean Gaussian process, we in the first chapter we proved that the sigma square is actually, the variance is actually equal to the second moment for a zero mean Gaussian process, and the variance is actually equal to the second moment for a zero mean Gaussian process, and this is the energy of the, this is the energy of the noise. This is the energy of noise. The variance is the energy of noise. Now we have to find out this variance, which is actually the which represents the energy of noise. And we would see that our expression, this expression becomes the signal to noise ratio. E over sigma can be expressed as the signal to noise ratio. Let's try to find out this expression. So we would be interested in finding out this n square term, expected value of n square. We can do so if you observe your expression for if you observe your expression R of t. Now you are familiar. Let me rewrite it so that it would recall your and if you see the received signal R of t, you transmit S of t, and the noise is added into it, right? When you multiply this one with S of t and integrate, which is the output of the correlator, you would get 0 to t R of t S of t dt, right? And this is actually equal to, we have proved that this is actually equal to the 0 to t s square t dt plus 0 to capital T S of t n of t dt. This is the noise term, this is the energy term, and this one is the noise term. This is our signal R, right? So we have we see this n of t. Now our n of t, if you observe this n, actually n, not n of t, if you observe this n, this is the integral 0 to t n of t s of t dt. This is n, right? When you say n square, you are actually multiplying n with n. So this is n square, and then we are taking the expectation of the n square, which is expected value of n square. So let me, whenever we have this kind of expression, the expected value of n square, we would define another n. Just with the change of variable, we can write the same n as 0 to t n of tau s of tau deta. Just changing the variable. N of t is equal to, you can say that t is equal to tau, right? So you can these are the same expression, just change of variable. Instead of t, we are using tau. Now this why we do this, it's just a fancy way of writing this n square. So if you want to write the n square, you can write the n square. N square would be this multiplied by this expression. So we can say, okay, we have n square, which is 0 to t, and 0 to t, n of t, n of tau, s of t, s of tau, and dt d tau, right? This is how we write our n square. Now we have to take the expectation. So the expected value of n square is same as the expected value of this right hand side. So the expected, now you can see that s of t is deterministic. S of t and s of tau, these are signals which are deterministic. The random process is given here, this one. So this expectation operation, it would operate on this random process. So we can just rewrite it as 0 to capital T, 0 to capital T, expected value of n of t, n of tau, s of t, s of tau, dt d tau. We can rewrite this expression here. You just say that, okay, the expectation operation, it operates on the random process. So now this expectation, expected value of n of t and n of tau, if you see the expected value of n of t and n of tau. N of t is the noise sample function. This is from the random process, and we know that the noise sample functions are independent. It's a random process, so n of t and n of tau would be independent. If they are independent, their expected value, the product of their expected value is 0, unless t is equal to tau. Unless t is equal to tau. When t is equal to tau, you can see, you can just substitute t is equal to tau, and you would get the expected value of n square, right? The expected value of n is square, which is the second moment. And the second moment of the noise, this expectation is actually equal to n naught over t delta t minus tau. Right? So this expectation is actually equal to this value, del n naught over 2 delta is a power spectral. If you recall it, this is actually the power spectral density. It's just an impulse, right? Or in other words, the two noise samples are independent. It's very similar to the concept of orthogonal signals. If you have two orthogonal signals and you want to find out the integral of their product, you would get 0. So n of t, n of tau, these are independent. If you, this expected value means the integral of this product. So if you want to find out the integral of this product, these are independent. For the independent signals, the independent sample functions, the integral would be 0 unless t is equal to tau. When t is equal to tau, this is the square of the signal. Square of the signal is the integral of the square of the signal is its energy, which you can get from the, we say that t is equal to tau, so here's the energy is n naught over 2, which is given by the power spectral density of the power spectral density of the noise. We have this function that for any frequency it is any frequency, it is n naught over 2. So this is actually n naught over 2. So if we substitute this n naught over 2 in the above expression, we would get n naught over 2 0 double integral 0 to tau, and then you have the okay, the expected value. We don't have a double integral because one integral goes with the one of the integral we have written. Let me rewrite it specifically and then I would solve it. 0 to tau delta t minus tau, right? Delta t minus tau s of t s of tau dt d tau. We are left with this one, right? We are left with this integral now. Now this product, you can see this one, this product, when delta t minus tau exists at t equal to tau. So at t equal to tau, you will delta t minus tau exists at t equal to tau, right? So at t equal to tau, this would be s square of t. So integral of the s square of t, the integral of the s square of t would be, you can just rewrite it as n naught over 2, and this integral, this is nothing but the integral of the square of the signal s t equal to tau dt, and you have 0 to tau, and this is the energy of the signal. So we can write this E n naught over 2. So this is the variance. The variance of the signal is nothing but the energy into n naught over 2. And if we substitute this now here, if this is your sigma square is E n naught over 2. So your sigma is actually equal to square root of E n naught over 2. Now if you rewrite your expression of probability of error, which is Q of E over sigma, it is Q of E over E n naught over 2, right? And this can be simplified. This can be simplified to be written as, this can be rewritten as Q of this is E square root E. You can rewrite it as 2 times E over n naught. So this is the expression for the probability of error when you are transmitting antipodal signals. This is the probability of error when you are transmitting antipodal signals. So if you transmit s of t or you transmit 1, this is the mathematical expression Q of 2e over n naught, right? So you can rewrite this expression like this. Now let's try. Now I think this is clear, right? You can just solve this one to become this expression, as you have E over, let me solve it, otherwise you would stuck in this step, which is very simple. Now you can write this E as the square root of E square root of E, right? Now you have square root in the numerator, square root in the denominator, so this would be cancelled, and you are left with square root of E and below n naught over 2, which is equal to whole square root E over n naught over 2, which is the same as 2 times E over n naught. So this is the probability of error expression, and if you observe this expression, if you observe this expression, which is q of 2e over n naught under the root 2e over n naught, and this e over n naught is actually the signal to noise ratio. This term e over n naught, this is the signal to noise ratio. So your probability of error is actually equal to square root of 2 times SNR. This is the energy of the signal. This is the noise power spectral density, which is actually the energy of the noise. In other words, energy of the noise. So signal to noise ratio, signal energy over noise power, signal to noise ratio. Now, if you observe this, I said earlier that if the value of x is greater, the value of x here is this one. If this is greater, the q of x is smaller. The q of x is smaller. So it means if your SNR, this is constant. So of course, if your SNR is high, if you have high SNR means less noise, more energy. Numerator bigger, denominator is smaller. So if you have high SNR, more signal energy is available at the receiver, less noise is there at the receiver, the error probability would be less. So for higher value of this this parameter, you have less value of probability of error. And if you plot it, if you plot this q of if you plot the probability of error, versus the signal to noise ratio. Signal to noise ratio, we usually take it in dBs. This signal to noise ratio is usually taken in dBs, and we get the probability of error. We get this error probability to be a decreasing curve. It's a decreasing curve, 0. So from 0 onward, as the error probability in the SNR increases, the error probability decreases. The error probability decreases for the antipodal signals. So this is the error probability for the antipodal signals. And usually at SNR 7 dB, SNR, you would see that the error probability is in the range 10 raised to power minus 3, which means 10 raised to power minus 3. 10 raised to power minus 3 means 1 in 1000. It means if you transmit 1000 bits, you would get 1 bit in error. So if the probability of error is 1000, you would get 1 bit in error. If your SNR is 0 dB, usually it is 0.5. So 0.5 means 1 over 2. So if you 1 over 2 means half of the bits will be in error. If your SNR is 0 dB, you would get this probability of error. This is the theoretical curve. If your SNR is 0 dB, the probability of error is 0.5, which means half. 0.5 is half. So half of your bits, if you send 1 megabits, it means that half of those bits would be in error. Its chances there, because you have a high noise, SNR is low, and if SNR is high, for example, up to 7 dB or greater than that, up to 10 dB, you are up to 10 dB or greater than 10 dB, your probability of error reduces. So it's quite important to analyze these plots. So this is the bit error rate curve. For antipodal signals. It looks like this. The bit error rate curve is monotonically decreasing curve. It's not monotonically decreasing, continuously decreasing curve. Now we derive this bit error rate expression. Or the probability of error expression, which is equal to q of 2 times e over n naught square root, which is equal to this one, by assuming that s of t is transmitted, right? Initially we assume that s of t is transmitted, which means that 1 is transmitted and we are getting a 0. So this is the chances that when you transmit a 1 and you would get a 0 at the receiver. For different SNR, you can observe those chances or that probability. You can derive the same expression when you transmit minus s of t. You would get the same expression, right? So actually the total error probability is contributed by the s of t as well as minus s of t. So the total error probability which is contributed by both s of t, or in other words, you may transmit ones and zeros, a sequence of ones and zeros and you always assume that in the sequence of ones and zeros, 1 and zeros are equiprobable, or they are both have the same, they are likely, both 1 and zeros are likely to be there. So usually in a suppose you have 1 gigabits, so we would expect that the number of ones and the number of zeros are equal. So when they are equal, both contribute equal error probability. So if we have the error probability, total error probability, half of it would be contributed by the probability of error when 1 is transmitted, and half of it, half of the total error probability would be contributed by the probability of error when 0 is transmitted. So when you compute this error probability of error, when now here if you specifically see, our expression is probability of error when 1 is transmitted. Similarly, you can get the probability of error when 0 is transmitted. So if we have the probability of error when a 1 is transmitted, which we just derived, s of t is transmitted, we say that it is q of under root 2 e over n naught, right? Similarly, for probability of error when 0 is transmitted, you would get the same expression. You can verify it, just go follow these steps and you would get the same expression. And when you say that the total error probability is half of these and half of PE given 0 plus half of probability of error given that 1 is transmitted. So it would again be equal to Q of 2 times E over N naught, right? So this is the total error probability which you get, which we derived earlier. So it's the same as this is the expression for the total error probability, whether you have a sequence of ones and zeros, or you just transmit ones or you just transmit zeros, you can get the same mathematical expression. So this is this is how we get the expression of the error probability. The error probability, the chances that we would get an error, or in other words, we would say that that gives us the knowledge that if we have certain SNR, if the SNR is available, let's say 7 dB, and the curve, the theoretical curve shows us that 10 raised to power minus 3 is the probability of error, which means that out of 1000, 1 bit would be an error. The chances that 1 bit would be an error, and so on. We can just observe the whole curve and we can see that for different SNR what is the probability of error.